Hi folks, welcome back. I hope you're all doing well. So by now we've seen that large language models, LLMs, are pretty good at generating prose. They're pretty good at generating code. But there's this entire field of computer science that tries to build automatic proof assistants. These are programs that try to formally express in a language mathematical proofs and then automatically check if those proofs are valid. So you might say those proofs themselves are code, and can we use LLMs to help with the generation of those proofs? And that is what this paper looks at. The system the authors have built here, called Baldur, uses an LLM to predict entire proofs. It is fine-tuned specifically on a data set of proofs. But on top of that, it also tries to fix the proofs that it generates that are not correct. This paper works with the Isabelle theorem prover, and its main contribution is to show that using LLMs, you can realistically generate proofs and get a higher rate of success than the two traditional methods used for generating such proofs. Those two methods are hammers, which apply heuristics repeatedly to see if you get a proof that works. And the second technique is search-based techniques, which take a partial proof and the current proof state, which is essentially what you know in your proof up to now. And they use neural network techniques to predict the next individual step and then apply that iteratively. They start with an LLM called Minerva, which is specifically trained on a corpus of mathematics. And then they take Minerva and fine-tune it for Isabelle proofs. The input to the proof generation model is the statement of the theorem you want to prove. And the output is an entire candidate proof. This is another notable difference from prior work. Most of the prior work generated one next step of the proof, whereas this system generates the entire proof of the theorem you're looking to prove. And once you have this candidate proof, you can feed it to Isabelle, which is the proof assistant, and it either succeeds, in which case you've proved it, or it gives you back an error. And for the case where the proof generation model generates a faulty proof that doesn't succeed, they have trained another model which is specifically for proof repair. And the input to this proof repair model is your theorem, the incorrect proof that the previous model generated, and the error message from the proof checker. And then this generates another candidate proof, and you can check it again and then iterate on it based on whether it succeeded or failed. Now, Isabelle is old enough and has a large enough library that you have a pretty large data set of existing theorems and their proofs in Isabelle. So that was used to train the proof generation model. But how did they train the proof repair model? They use that same ground truth training set and take the theorems from that set and feed it to the proof generation model. And for the cases where the proof generation model generates an incorrect proof, they take the error message, the faulty proof, and combine that with the theorem and the ground truth proof. This is the proof that already existed in the library as input training data for the proof repair model. So that's a clever way to generate lots of examples to train the proof repair model. And then you can do one more optimization to give your LLM some more context. Usually when you're trying to prove a theorem, you won't have simply the statement of the theorem you're trying to prove. You'll also have some background lemmas or preceding theorems in the same file. And you can add all that as context to the prompt that you're giving the LLM. So here are the results they got. You can see that they've trained two models, one with 8 billion parameters, one with 62 billion parameters. And you can see how their success rate is increasing as they incorporate additional steps like the repair model or adding more context and then increasing the size of the model. The best result they get is with the large model with context, and that gives them nearly a 50% success rate. But interestingly, if they combine it with Tor, which is the best traditional automatic prover they have, they get a success rate of more than 65%. And that, by the way, is higher than Tor on its own would have been able to achieve. Now, the next question to ask is, did building a proof repair model help? Was that worth it? And what they found is that yes, it did help. In this graph, on the x-axis, you have the number of proof attempts. On the y-axis is the success rate of the generated proofs. This red line shows the success rate using both the proof generation and then the proof repair models. And you can see that this red line is always higher than the blue line, which uses only the proof generation model. But they did one more interesting thing, which is that they trained a proof repair model, but omitted the error message of the unsuccessful proof from the training data. And you can see that in this brown line on this graph. And the success rate of that repair model is the same as if you had only used the purely proof generating model, which goes to show that it was these error messages that were giving the LLM additional context to be able to do better than just the generation model. So that was a quick look at a paper that tries to train a large language model specifically for automated theorem provers and applies it to this new domain and shows that yes, indeed, LLMs can be used to push the state of the art in automatically generating proofs for these automated theorem provers. I hope you enjoyed that. If you enjoy content like this, please consider subscribing. Please like the video, and I will see you all next time. Thank you.